Hold on. Okay, so we've got this situation where we have an object. In the last couple of videos, it was, the eye of our stove. But I want you to notice, and what we're doing is we're turning the temperature up. And as we do so, it emits more and more and more light. And it also produces higher and higher frequency light. So notice here, down when we had our eye of the stove off, and it was at room temperature, 300 kelvins, our F max was down here. This little, I've marked F max along the x-axis, right there where that orange line is down there, right? That's the value along this line here. That's F max at 300 kelvins. Then we turned the temperature up, and the spectrum shifted to the right and got bigger, and our new F max, right here, our yellow one, hold on, let me get my colors here. The new F max there shifted up. You see that? It shifted from the orange mark on the x-axis to the yellow one. And then we turn it up further, and F max again shifted to the right, so that now we moved to there. And finally, we cranked it all the way up to 20,000 kelvins. Our F max is now way up here, and the F max shifted again. The point here, and it's not obvious in the picture, but the point I want to make is that F max, which tells you kind of the average frequency of the light. Think of it like an average. Simplest way to think about it. Okay. F max is kind of like the average frequency of the light emitted by the eye of the stove. Turns out that F max is proportional to the temperature in kelvins now. In kelvins, not degrees Celsius, not degrees Fahrenheit, not that weird degrees Rankine thing. Kelvins. They are proportional. So if you double one, you double the other. If you double one, you double the other. Okay? They are proportional. So if I increase my temperature, if I take it from 300 to 600 kelvins, then my frequency of maximum emission shifts from one value to twice that value. Okay? If I cut my temperature in half, if I go from 300 kelvins down to 150 kelvins, then the frequency of maximum emission, that average frequency, also gets cut in half. Now, it's usually, this is not quite enough information. I want you to remember that in general, frequency is c over lambda. That's how frequency, speed of light, and lambda wavelength are connected, you remember. We can combine these two facts together to get what we call Wiens displacement formula. Wien or Wien, however you want to say it. We get Wiens Now why it's called this is not important. Again, it's kind of a historical rabbit hole. Wiens Displacement Law. And it relates to temperature and the wavelength. Okay, let's actually do it this way. F max is c over lambda max. Right? Because with light, if I give you a frequency, you can give me a wavelength. They go together because c is a constant. So if f has a set value, lambda's got a set value. So for every f max, there is an associated lambda max. Okay, that's how they're connected. So I'll write it over there. I'll write it here also. F max equals c over lambda max. So instead of talking about the average frequency of the light emitted by the eye, we can talk about the average wavelength of the light emitted by the eye. Okay, two ways of saying the same thing. They're related by the constant c, the speed of light, right? So we can use either one to describe the light. Now, the plot I made used frequency. I could have made a plot using wavelength. I just like the frequency plots better. I think they make more sense in a teaching style, in a teaching context. But I could have also made a wavelength plot. Okay. That displacement law is given by this formula right here. Lambda max times t is equal to a constant, 0.2898 times 10 negative 2 meters times kelvins. Okay, let me put a little box around that. Wiens Displacement Law. Listen to that marker sing. Yeah, baby. Okay. So basically, if I give you a temperature, you can give me an average wavelength. If I give you an average wavelength, you can give me a temperature, because this on the right-hand side, there's no name for that constant that I'm aware of. There might be one. I don't know what it is. But the point is, if I give you lambda max, you can give me T. If you give me T, I can give you lambda max. Okay. They go together like that. So if we use this formula, for example, at 300 kelvins, let me pick a different color here. I think the pink's getting a little tired, I believe. So let's say at 300 kelvins, okay, lambda max equals 0.2898 times 10 to the negative 2 meters times kelvins over, I'm just dividing both sides of this by T, over 300 kelvins. This is at 300 kelvins, at room temperature. And if you do the maths, see the kelvins are going to cancel, you're left with meters, and you end up with 9,700 nanometers. 9.7 times 10 to the negative 6 meters. Okay, that's 9,700 nanometers. This, of course, is way outside of the window of visible light between 400 and 700 nanometers. It's far higher than that. So this is obviously infrared, as advertised at 300 kelvins on the plot. Okay, you can do the same math to show yourself that at 1,000 kelvins and 5,600 kelvins and 20,000 kelvins, the wavelength is going to decrease as we go up in temperature. The average wavelength, the frequency will go up, right, as shown on the graph. But if the frequency goes up, the wavelength goes down. So at 1,000 kelvins, lambda max equals 2,900 nanometers, which is still outside the range of visible light, right? Visible light is 700 to 400 nanometers. And I want you to memorize that. I want you to know the range of visible light, 400 to 700 nanometers. I'm not going to, you have to know that, okay? It's one of those things, I'll meet you on the corner in downtown Decatur 15 years from now. I'm going to ask you what's the range of visible light in nanometers, and you need to say 400 to 700. Purple to red. So this is outside the range. This is also IR. But if we go to 5,600 kelvins, we'll get lambda max is equal to 520 nanometers, which is green. Yellow-green. Okay? Visible. And finally, at 20,000 kelvins, our peak wavelength, our average wavelength, is 140 nanometers, which is, of course, way shorter than 400. We are now into the ultraviolet. Okay. We are now into the ultraviolet. Now this lecture is getting a little bit long, but I do need to add one last really important thing. Okay, when this was discovered back in the 19th century, it didn't make any sense. Okay, the details of how it didn't make any sense, I'm not going to get into. It was something, if you ever want to know about it, Google the Ultraviolet Catastrophe. Okay, that's actually what it's called, the Ultraviolet Catastrophe. And it was a catastrophe. This whole thing I'm presenting to you was a catastrophe because it didn't make sense in light of, get it? In light of what was known about light at the time. Thinking about light as a wave, it didn't make any sense. That it led to a logical contradiction, and it just completely destroyed any model that people had about light, what we now call a classical model of light. It didn't work. There's only one way to reconcile this result, everything I've said in the first 3 lectures, and that was to say that light sometimes acted like a particle of energy h, let's get back to h in a second, times the frequency. In other words, the energy of a light wave, of light, was proportional to its frequency. And we talked about this equation a little bit earlier on briefly, but here it is back again. I'm going to put 2 boxes around it. The point is, I'm looking through a little window here at you, is that light acted like a particle. Okay, we'll get more of the particle business in a second, but this is the first hint that something was wrong with our theory of light. And the energy of light had to be proportional to its frequency. We'll get to the particle thing in a minute. I don't want to get ahead of myself with that. This is the first hint that the energy of light was proportional to its frequency. Before this, it was thought that the energy of light was proportional to its amplitude. Okay? That is, how high the light wave was, not what its frequency was. Okay? So this is a result that came from this so-called ultraviolet catastrophe, the details of which I'm sweeping under the rug. But this is the formula we're left with. Okay? E equals HF. And H is 6.63 times 10 to the negative 34th. Yes, that's negative 34th joules seconds. Okay, a quantity known as Planck's constant, and I believe we have mentioned this before. In at least one of our sections I have mentioned, I think, maybe probably both of them, Planck's constant. Okay, it's just a constant for our money right now. It's a super important one, but it's just a constant. So if you increase F, you increase the energy. Energy is proportional to frequency, not to amplitude. This was the first indication historically that our old models of light weren't working very well. Okay, this whole result in the first 3 videos, okay, was a result that was not expected, and that insisted that something about light, that we were missing something about light. Oh, this is also UV. That's it for this one. We'll pick back up with this whole light mystery thing next.